Hi, this is Miss Park. Our topic of today is annuities. We've already seen compound interest examples. We've seen how money grows in the bank as it earns compound interest. With compound interest questions, we've always had a beginning amount and then some length of time passes, and then we have an ending amount. Usually, when we save up to buy things, we don't put money in the bank now and then just wait until the end. We usually continue to add money into the account over time. So, for example, suppose you want to save up to buy a car, and you'd like to buy a car at the end of 2 years. So you might decide to put away a certain amount of money every month. So that would be an annuity. An annuity is making multiple payments at regular intervals of time. So let's say I'm going to put aside $300 every month. Okay, so that would be an annuity. Suppose you knew how much money you wanted to save up for in the future. So let's say you know a cruise or a house or uh, you know uh, taking a course, going to university or anything like that. Suppose we had a money amount for the future, then you could create an annuity for building up so that at the end of whatever period of time you have the amount that you need. So that's what we're going to be doing in this lesson. Annuities are also they come up when you pay off a loan. So let's say you wanted to buy something today. Let's say you wanted to buy a car. You're not quite there yet, but hopefully you will be someday. But you don't have all the money for the car. So you buy the car today. The store or the dealership you're buying the car from gets their money today because you will go and get a loan from the bank in order to pay them. So they will get their money today for the car, but then you are left to pay off the loan. Okay, so when you pay off the loan, it's going to be over a period of time, say a few years, and you're going to make regular payments, the regular intervals of time until you have paid off the whole loan. And another way we can use annuities is if, let's say, you're going to retire. So somebody who's going to retire is not going to work anymore. They can't depend on income coming in. So what they do is they take what's called their retirement savings. So all the money that they have, they put the money into the account today so that as the money grows over time, they can pay themselves like a salary every month. So let's say I put in a large amount of money today, and then every month I can take out some money from the bank, the same amount every month, kind of almost like a paycheck, but it's coming out from the bank account. Okay, so all of those are annuities. So the idea with annuities, so I'm going to use the booklet page here. So an annuity is a sequence of equal payments made at equally spaced intervals of time. So not to be confused with the compound interest questions, which were a one-time payment. Okay, so these is a sequence of payments. Some language here. The term of an annuity is the total time involved in completing the annuity. So let's say you want to save up some money in order to buy a car in 2 years, then the term of the annuity is 2 years. And in our course, we're only involved with ordinary simple annuities. Ordinary simple annuities means that the number of payments is equal to the number of compounding periods. So if the interest rate is being compounded monthly, then you're also making monthly payments. Those will always match. And the payment is made at the end of each compounding period. So if you come across a word problem that talks about the end of the compounding period, you can kind of ignore that because all of our questions are ordinary simple annuities. All of them are being paid at the end of the compounding period. Okay, so let's do a quick example here to see how money grows as an annuity. So we've seen a timeline before in compound interest. And let's read. Derek invests $500 at the end of each year for 4 years. All right. It's not once, it's at the end of each year. So which means it's more than once. It's every year he's putting $500 for 4 years. If interest is paid at 7% per annum compounded annually, how much will the investment be worth once the last deposit is made? Okay, so he is making 4 deposits of $500. Now, 4 deposits of $500 does sound like 2,000, 4 times 500, but it will be more because the money will earn interest while it's in the bank over 4 years. So how much will it be altogether? So let's see. So let's say this was 2006 he started. He made a payment, a payment, a payment, and a payment. And then at the end of this 2009 year, let's see how much money he's going to have. What happens is each of these payments has been sitting in the account earning interest. This last one was made at the end of the last compounding period. So it actually has not earned any interest at all. This is the right at the end. So the future value of this payment is $500. And that's it, because that one has not grown. Whereas this one that was done at the end of 2008 was $500, and it has been sitting in the account for a year. So the future value of that $500 is $500 times 1.07, right? It has grown by 7%, so that's $535. Now, this one has been sitting in the account for 2 years. So it's actually accumulated 2 years worth of interest. So that one is 500 times 1.07 squared. And that's 572.45. And this one, which was the first payment that was made, has been sitting in the account for 3 years. So that one is 500 times 1.07 to the exponent 3, which is 612.52. And now when you add up the values, the ending values of each of these payments, you add them together, you get the amount in the account after the 4th year ends. Okay, and so now what does that mean? So he's put money into the account. Hopefully he's earning interest. So how much interest has he earned? So let's see, he put in $2,000. Why $2,000? Because it's 4 payments of $500. That's how much he put in. The rest has been interest. So it became 2219.97. Therefore, he earned the difference in interest. So the difference is 219.97 in interest. Okay, he put from his pocket $2,000, but it ends up being worth 2219.97. So he's earned that in interest. All right, so now we're not going to do a timeline like this for every single question. We have a formula. So this is a formula for future value of an annuity. And it looks just like geometric series, because look what this is. This is a geometric sequence. When you add them all up, you get a geometric series. So the formula comes right from geometric series. R is the regular payment. It's the amount that you pay every month or every compounding period. It's also the A value in the geometric sequence. Okay, 1 plus I to the n, that's our 1 plus, that's the same as the geometric sequence, the R to the n. So R is the rate of growth, it's exponential. So it's 1 plus the rate of interest per compounding period. Here's our minus 1. And here's our R minus 1. So our rate of growth, so in this case would have been, we're multiplying by 1.07. When you subtract 1, like from the geometric series, you get just the 0.07. So it's divided by I. You can see that that's where it came from. And then the I and the N are exactly like in the compound interest formula that we've seen. All right, and that's how annuities will grow over time. There's another thing called the present value of an annuity. Okay, so the present value of an annuity is, again, there's an annuity and it's being, there's deposits over time or payments over time, same thing, but the present value is how much is that money worth today? All right, so for example, if somebody was to put in money into an account so that they could pay themselves an income over the next, say, 20 years, how much money should they put in the account today? That's called present value. Versus, I want to save up to buy a car that's $20,000 5 years from now. That $20,000 is called future value. So present value is today, how much is it worth? Okay. Also, if I wanted to buy something and have a loan, so let's say I wanted to buy a car, I'll just keep using the car example. Suppose I want to buy a car today and I don't have the money, so I take out a loan. Because the car store gets their money today and the loan is my problem, the value of the car is the present value of the loan. So that's the amount that's owed today. But because I'm going to be paying it over time, of course, I'm going to be paying a lot more than that because I have to pay interest on that loan. So there's a similar formula for present value. Okay, so you just take a moment to compare how they look. The variables are the same, but the formula is a bit different. I'm going to do a quick example with present value. Okay, so in class, we talked about the lottery that is paid out over regular periods of time. So in this case, Derek wins $10 million in a lottery, but instead of giving him $10 million right now, he's going to get yearly installments of $500,000 for 20 years. It means he's going to get $500,000, so $500,000 for 20 years. This makes $10 million, but the $10 million is going to be over 20 years versus today. So it's actually not as good. $10 million today is worth much more than $10 million spread out over the next 20 years. So what is the present value of his winnings? So what is $500,000 times 20 years worth today? Assuming that he can earn 10% interest compounded annually. So let's figure it out using the present value formula. So like always, we're always going to write the formula first and then input the values, okay? And as always, we're always going to write our variables on the left-hand side so that we don't miss anything, and we're very careful and we show that we understand what the variables mean and what goes into them and how to put them into the formula. So a regular payment is 500,000. Your little I is 0.10 and it's compounded annually, so I don't have to divide it by anything. And N is just, it's once a year for 20 years. All right, so now I'm going to put it into here. So this is 500,000 times 1 minus 1 plus 0.10 to the negative 20 over 0.10. Okay, and you can actually put this into the calculator all at once. Just be careful with the brackets. So please check with your calculator. If you want, pause the video right now. Try this with your calculator. Make sure that you get the same answer as me. Okay, so it works out to be 4256781.86. And we always answer in a sentence. So the present value of his winnings is 4,256,781.86. And we can see that that's a lot less than 10 million, which means that if he took the yearly installments, then they're really only worth this much today. So whatever they offer him as a lump sum, he can compare to this because that's what his payments are going to be worth today. Okay, so once again, how do you recognize an annuity question from a compound interest question? Is that the annuity question has regular payments over time, so more than one payment, and the compound interest question has only one payment at the beginning. And how do you recognize future value from present value? So that's going to be from the language in the question. Whether they're asking for how much something is worth today or whether or how much it's worth in the future. So please stay tuned for part 2 that has examples of using the examples of word problems with future value and present value of annuities. Thanks for watching.